Hello everyone, my name is Wang Yuan. Today I'm going to talk about application of Ising model in quantum annealing. The reason why I chose this topic is because we have talked a lot about Ising model in our classes, and to me, a total stranger to quantum algorithm and quantum computing, quantum annealing is a very interesting and surprising topic. In the very beginning, I actually thought these were a fraud or a joke, like we say, 遇事不决, 量子力学. You got a problem and you solve it quantum. But it is actually one of the most promising quantum algorithms so far. It is very useful as well, theoretically. And I hope I can give you a rose picture of it through this brief introduction. Here is the table. I'm going to talk about what is quantum algorithm and its characteristic compared to its classical counterpart. And I will talk about QUBO problem, which is used to represent many kinds of combinatorial optimization problems, and I will talk about quantum and annealing. Later, I will further talk about how to transform QUBO type problem into Ising model form. I will compare with its classical counterpart, simulated annealing. In the end, I will show an example of application of quantum annealing. In order to realize how special is quantum algorithm, we need to talk about its classical counterpart. And we need to realize the differences between deterministic and non-deterministic computation. Like this figure I show you, the deterministic computation, every single state is followed by only one state. In the other hand, the non-deterministic one, a step may be followed by a new step. This kind of parallelism is just like superposition in quantum mechanics. Instead of existing in a single one state, a quantum system is initials in a superposition. This allows the hardware to process the probability amplitudes of all possible solutions simultaneously, unlike the deterministic computation can only process one by one. Here are two examples of two of the most quantum algorithm for now, Shor's algorithm and Grover's algorithm. They are aimed to solve different problems. For Short, integrated factorization. For Grover's, unstructured search. And it has some advantage compared to its classical counterpart, but we need to be really careful. These advantages actually only happen in very strict condition or a very specific classical counterpart. The classical algorithm is actually still progressing. And technically, it is sometimes very hard to say there is an obvious advantage, because some predict you need like a million of qubits to see obvious and meaningful differences between classical and quantum algorithm. And the quantum advantages are not always that can significantly speed up or lower the complexity. It might have advantage in a sense that you can find better suboptimal solutions, or in a given time you can have a higher chance to get a solution with a lower error. A QUBO problem, quadratic unconstrained binary optimization problem, is an unified mathematical framework used to represent many kinds of combinatorial optimization problems. Like in finance, you want to build out a portfolio based on stocks in SP 500 index. You can have many choice, like you want to at least choose 50 stocks, and you can take 51, 52, 53 along to 500. So you need to compare your portfolio with roughly 2 to the power of 500 version. So yes, combinatorial optimization problems are a set of very hard problems. It has a lot of applications in logistics, finance, or graph theory fields. So it is always nice to have a better algorithm to improve the calculations. And here, equation 1 show QUBO problem can be written as equation 1. It already looks like our familiar Ising model forms, but there is some differences. In computer science, their variables choose 0 or 1, unlike us, we choose 1 or -1. And those like interaction coefficients have another meanings, unlike physics. A QUBO problems asks us to solve for the binary vectors that minimize the function, and it acts very like how we solve minimum energy in Ising model. I think in this proposal, we only need to know how do they write down a QUBO problem. There are actually many things to consider so that they can transfer into Ising model 4. But it is actually a little too hard, and it is really depends on the questions and the device you use to do the calculation. Therefore, I won't talk about it in this representation. And the real Hamiltonian in quantum annealing we will use is a combination of initial Hamiltonian and Ising Hamiltonian. The initial Hamiltonian is actually a transverse field Hamiltonian, which dominate the Hamiltonian in the very beginning of the annealing. And in the end, the whole Hamiltonian will become just the Ising Hamiltonian. And just like QUBO problem, quantum annealing is to design to find the ground state of an Ising model. And by some very restricted and complicated derivations, if the transition is slow enough, the system remains in the ground state, ending in the optimal solution of problem Hamiltonian. And the mathematical deviations of changing QUBO problem to Ising model form is to do the change the logic binary variables into the spin one through the third equation. And it is actually a very hand-waving derivations. There are actually many problems, like in the field of computer science, they actually allow QUBO problem has higher order terms like third order. But there are two mainstream solutions for that to reduce higher order into standard Ising model form. And again, my goal is to show, we can transform in QUBO problem into Ising model form so that we can solve it with quantum mechanical way. And let's take a head-to-head comparison with its classical counterpart, which is usually called simulated annealing. And you can see the control parameter part. In simulated annealing, they control the temperature parameter. So that's why this process called annealing. It is very interesting to me, and their physical principle is very interesting. And simulating annealing, they explain this temperature as thermal fluctuations. That's how, and that is the reason why it can travel between many suboptimal or optimal solutions. And to quantum annealing, the reason why the state can travel between two suboptimal or optimal solutions is use quantum fluctuations. And the control parameter is transverse field. And in the end, the strength of the transverse field dropped to 0. So the state stopped tunneling, and it stopped at a suboptimal or optimal state. And you may see this figure too. Each method performs better really depends on the question and the device you use. The landscape with broad, wide barriers is more suitable to use simulating annealing to solve. So yeah, just like what I said, the discussion about quantum advantages is very subtle. Sometimes it outperforms, sometimes the classical one outperforms. And to quantum annealing, the width of the barriers can be measured by the differences between the first excited state and the ground state. Usually, if it has a smaller energy differences, it can outbid classical annealing in a sense that in a given time, it had a better chance to get an optimal solution, unlike instead of a suboptimal one. In the end, I give an example of minimum multi-code problem. It is a well-known NP-hard problem, and it can be related to many number series problems. So I think it's a nice idea to show it. And the more interesting thing is this result is generated by a annular of the wave system. It is a real device. Let's define what is a minimal multi-code problem first. This problem is actually like a childhood gameplay. You have some spot and you connect them with line. And let's check you need how many cut to cut off all the line. And here is a little difference that there is some penalty wave. So it is actually a constraint system. So yeah, it is actually a powerful method. You can actually solve a constraint system as well. In this paper, a cross-disciplinary introduction to quantum annealing-based algorithm, they try example a tree with 20 vertex and 10 terminal pairs. In their setting, they say they need to cut off 5 lines. But I actually think the more important thing is that how do they quantify their performance. The gauge average total time we need to ensure a 99% success probability with 700 microseconds for each annealing is 56.65 seconds. It's a pity that I can find a classical counterpart, but I'm still glad to see how experiment conduct. And this is the end of my representation. I hope you can capture some picture of quantum annealing, and I wish you a great winter vacation and Happy New Year.